Hey guys, welcome to another video, and this time we're going to discuss Riemann sums. So this was formulated by a German mathematician named Bernhard Riemann in order to estimate the area under a curve using rectangles. So these rectangles have an equal width of delta x, and their heights depend on which subinterval you are going to use. You can either use the left endpoint of the subinterval, the right endpoint of the subinterval, or you can also use the midpoint of the left and right subintervals. Afterwards, you get the sum of those rectangles in order to get the approximate area. Let's define the terms so that you will not be confused. So first we have x sub I, which is the sample point in the subinterval. Then we also have delta x, which is the width of the subinterval, and it is also the width of the rectangles. We have b as our upper limit and a as our lower limit. And lastly, we have n as the number of subintervals. So usually in the problems, this n is given. So with the formula of determining Riemann sums, we have the summation of f of x sub I star. So star meaning this can be any point in the subinterval. So this can be from the left endpoint, right endpoint, midpoint, or any other point in that subinterval multiplied to delta x, or the width of those rectangles. And that delta x is equal to b minus a divided by n. So in order to further understand Riemann sums, let's do some examples. So first, let's use left endpoints. So when using left endpoints, the height of the ith rectangle will be f of x sub I. So what does that mean? So let's first read the example. So determine the Riemann sum of f of x is equal to x from 0 to 4 using 4 intervals. So this is our n. And in order to get delta x, we use the formula b minus a divided by n. So b, the upper limit is 4, the lower limit is 0, and the number of intervals is 4. So 4 minus 0 is 4, and 4 divided by 4 is 1. So from here, we can say that each of the approximating rectangles that we will use has a width of 1. Now that we have our delta x, we can now write our subintervals. So first we have from 0 to 1. Then we have from 1 to 2. Next we have from 2 to 3. And lastly, we have from 3 to 4. So now that we have our subintervals, let's choose all the left endpoints. So we have x is equal to 0, x is equal to 1, x is equal to 2, and x is equal to 3. So we are going to use these endpoints in order to find the height of the approximating rectangles that we will later then add up in order to get the approximate area. So what we have to do is to substitute these values of x into our function f of x in order to get the height of the approximating rectangles, and then multiply them to delta x, which is just equal to 1. So let's do a shortcut here. So this becomes, using the left endpoint or the first left endpoint 0, we have f of x is equal to x or just 0. And 0 times 1 is just equal to 0. Then add our next endpoint, which is 1. So when x is 1, y is also 1. So that's 1 times 1 or just 1. Using our third left endpoint 2, substituting 2 from x will give us f of x is equal to 2. Multiplying it to 1, this will give us 2. And the same with our last endpoint 3. When we substitute 3, we will just get 3. So the approximate area using left endpoints is equal to 0 plus 1 plus 2 plus 3, or just equal to 6. So 6 units squared is our approximate area for f of x is equal to x from 0 to 4 using 4 intervals. So this is while using left endpoints. So now let's try using right endpoints and see if we can get a different answer. So delta x here will be the same since we have the same function, same interval, and same number of subintervals. The only difference is we're going to use right endpoints. So for delta x, we have b minus a divided by n, or 4 minus 0 divided by 4, which is still equal to 1. So our subintervals would be 0 to 1, 1 to 2, 2 to 3, and 3 to 4. But this time, instead of using left endpoints, we're going to use right endpoints. So our right endpoints in our subintervals are 1, 2, 3, and 4. So now let's write the formula or the summation or the sigma notation for the Riemann sum, which is the summation of f of x times delta x from I is equal to 1 to n, which is equal to 4. So here we have our delta x as 1 multiplied to f of x. So for our first right endpoint, we have x is equal to 1. So this gives us f of x is also equal to 1. So plus, using the second right endpoint, so we have f of x is equal to 2 times dx, which is 1, plus the third right endpoint. So substituting that 2x will just give us 3, multiplied by the delta x again, or the width of the rectangles, which is equal to 1. And lastly, substituting the last right endpoint, which is 4, gives us 4 times delta x, which is 1. So adding them all up, this is just 1 plus 2 plus 3 plus 4, which is equal to 10. So now we have 10 units squared as the approximation of the area using right endpoints. So as you can see, using left endpoints we got 6, and using right endpoints we got 10. And now let's compare what approximate area we will get when we use midpoints. Let me rewrite the equation for delta x again, which is equal to b minus a divided by n. which is equal to 4 minus 0 divided by 4, giving us delta x is equal to 1. And we still have the same interval from 0 to 1, from 1 to 2, from 2 to 3, and from 3 to 4. But now what we are going to use are midpoints. So in order to get the midpoint, what we have to do is to add the left and right intervals and divide them by 2. So 0 plus 1 divided by 2 is 1 half. 1 plus 2 is 3 divided by 2 is 3 halves. 2 plus 3 divided by 2 is 5 halves. And 3 plus 4 divided by 2 is 7 halves. Using these midpoints in order to compute our Riemann sum, we get the summation of f of x times delta x from I is equal to 1 to I is equal to n, and our n is equal to 4, equal to, so let's write first delta x, so that is 1, times f of x, substituting 1 half to f of x just gives us 1 half, plus 1 times our second midpoint, 3 halves. So substitute this to the function f of x, we still get 3 halves. So 1 times 3 halves, plus our third midpoint, 5 halves. Substitute to the function f of x is equal to x, we'll still get 5 halves. So 1 times 5 halves. And lastly, for our last midpoint, 7 halves. Substitute that to the function f of x, we get 7 halves times our delta x, or the width of the rectangle. So this will give us 1 plus 3 plus 5 plus 7, so that's 16 divided by 2. Simplifying this gives us 8 units squared. So this is our area approximation for the function f of x is equal to x using midpoints. So comparing, using left endpoints, we get 6 units squared. Using right endpoints, we got 10 units squared. And using midpoints, we got 8 units squared. So as you can see, adding the approximate area using left endpoints and right endpoint, 10 plus 6, which is equal to 16, and divided by 2, that gives us 8 units squared. So it is possible that we no longer have to do the computation for midpoints as long as we know the areas for the left endpoints and the right endpoint Riemann sums, and just divide them by 2. So now that we have those 3 approximate areas, how do we determine the exact area without using integration? So when we graph this function in the Cartesian plane, what we get is a triangle with a height of 4 and a length of 4. Rather, we have the base, which is equal to 4. And what is our formula for the area of a triangle? So we just have 1 half base times height. And 1 half times the base, which is 4, times height of 4. This is equal to 4 times 4 is equal to 16 divided by 2, which is 8. So among the three Riemann sums using midpoints is the most accurate. And now to further enhance your mastery of this topic, let's do some additional examples. So another example for left endpoints. Determine the Riemann sum of f of x is equal to x squared plus 2 from 0 to 2 with n is equal to 4. So here we're going to use 4 rectangles of equal width delta x, and delta x is equal to b minus a divided by n. So b is our upper limit and a is our lower limit. So b is 2 minus a 0 divided by n, which is given, that is equal to 4. Simplifying, we get 1/2. Writing those intervals, we get from 0 to 1/2. Next, we have from 1/2 to 1. Then we have from 1 to 3/2. And lastly, we have from 3/2 to 2. So using these left endpoints to get our Riemann sum, so we get the summation of f of x times delta x from I is equal to 1 to I is equal to n, which is equal to 4. So this gives us 1/2 times f of 0 plus 1/2, which is our delta x, times f of 1/2 plus 1/2 times f of 1 plus 1/2 times f of 3/2, or our last left endpoint. So this gives us 1/2 times 2 plus 0 squared plus 1/2 times 2 plus 1/2 quantity squared plus 1/2 times the quantity 2 plus 1 squared, and lastly plus 1/2 times 2 plus 3/2 quantity squared. And adding these all up, we get 23/4. So this is our Riemann sum using left endpoints with 4 subintervals. Next example would be right endpoints. So determine the Riemann sum of f of x is equal to 1 plus 2x from 0 to 4 with n is equal to 4. So we've been dealing with this subinterval for quite a few examples. So we have 4 minus 0 over 4, or delta x is just equal to 1. And our subintervals, we have 0 to 1, 1 to 2, 2 to 3, and lastly 3 to 4. So what we are going to use are right endpoints. So let me just circle them in order for us not to get confused. So there, let's write the formula or summation notation for Riemann sums. So we have f of x, the summation of f of x times delta x from I is equal to 1 to n, or the number of subintervals, which is equal to 4. So this is equal to 1 or our delta x times f of 1 plus 1 or delta x times f of 2 plus 1 times f of 3, and lastly plus 1 times f of 4. So this gives us 1 plus 2 times 1. So let's ignore the ones. So they can be cancelled anyway, or they can be ignored. Plus f of 2, which is 1 plus 2 times 2. Plus f of 3, which is equal to 1 plus 2 times 3. And lastly, plus 1 plus 2 times 4. So what we did is we just substituted our right endpoints to the function f of x in order to get the height of the rectangles. Then multiply them to the width of the rectangles, which is 1. So simplifying this becomes 1 plus 2, which is 3, plus 1 plus 4, which is 5, plus 1 plus 6, which is 7, plus 1 plus 8, which is equal to 9. So adding them all up gives us 24 units squared. So this is the Riemann sum of f of x is equal to 1 plus 2x from 0 to 4 with n is equal to 4. So for our last example using Riemann sums, we have determined the Riemann sum of f of x is equal to x squared minus 1 from 0 to 4 with n is equal to 4. Again, we have the same subinterval, so let me just write that quickly. So we have from 0 to 1, from 1 to 2, from 2 to 3, and from 3 to 4. So what we are going to use are midpoints. So 0 plus 1 divided by 2 is 1 half. 1 plus 2 divided by 2 is 3 halves. Then we have 2 plus 3 divided by 2, 5 halves. And 3 plus 4 divided by 2, 7 halves. So using summation notation for Riemann sums, so we have the summation of f of x times delta x from I is equal to 1 to I is equal to 4. Then we have delta x, which is equal to 1 times f of 1 half plus 1 times f of 3 halves plus 1 times f of 5 halves and 1 times f of 7 halves. So you do not need to keep writing 1 for delta x. I'm just doing that as a habit so that I do not forget to multiply f of x by delta x. But we can ignore that for now since delta x is just equal to 1. So this gives us 1 half squared minus 1 plus 3 halves squared minus 1 plus 5 halves squared minus 1, and lastly plus 7 halves squared minus 1. So this gives us negative 3/4 plus 5 over 4 plus 21 over 4 and plus 45 over 4. So simplifying, this gives us 17 units squared. So this is our final answer for the Riemann sum of f of x is equal to x squared minus 1 from 0 to 4 using midpoints with n is equal to 4. So what we keep getting are just the approximations for the areas under the curve using approximating rectangles. But approximations aren't that useful in terms of engineering where accuracy and precision is required. And how do we achieve that exactness? How do we go from approximate to exact? So what we do is to let n, or the number of subintervals, approach infinity so that the width of the rectangles closely approach 0. And as that approaches infinity, that approximation now becomes exact. So we define this limit of Riemann sums as n approaches infinity as our definite integral. That is all for this video. If you learned something, please leave a like. Or if you are having troubles with any of the topics discussed, leave a comment down below. And as always, I will see you on the next videos.